Well, it's my pleasure to present Alejandro Merlo. Oteo, he's been working on Gaia theory for some time now. He was a devoted student of the content that we researched in this group before he met any of us. And in a different parallel life he has. And at some point our worlds crossed or collided, I'm not sure. And he started his PhD with us. And well, as the natural evolution of this research topic, he connected with the contemporary anxiety having to do with global warming and the ecological and social and political crisis we live today. This research he has presented elsewhere, in Complutense University, in Cornell Lawrence Institute, at the Royal Society in London. And as you can see, the most important is today he has research more than the Royal Society. He will have the time today to expand in more detail his presentation. And it's a good opportunity for him to receive feedback because this is a paper that is still work in progress. It will be completed soon, so please don't hesitate to make contributions that help him improve the paper and the ideas. And I think it's a fascinating topic. You will see, open to many debates. So I'm sure we're going to have a nice discussion after. So I hope most of you already had something for lunch, and we can enjoy a prolonged conversation. In any case, we can also have a drink or a coffee or anything later on. The title of his talk is "How is Global Warming Bad for the Planet? A Perspective from Theories of Biological Organization." Obviously, the ones that been worked out in this group. Yeah, the stage is yours, Alex. Congratulations for bringing us a new set of ideas after the thermodynamic tendencies of the planet. Thank you very much.
Thank you. Yes, so indeed, my topic is global warming and trying to make sense of global warming as a way of referring to the contemporary climate crisis and so on. And it's a topic that interests me, that led me to want to start a PhD, because I found there were some background ideas and some common ideas that were circulating, but which were not completely philosophically clear and which merited some investigation, some research, and that theories of biological organization could help with it. So I start with just a selection of pictures where you can see this recurring idea that there is something going on that is not good for the planet, that is bad for the planet, that is harmful. I'm referring to the ecological crisis, but it's something that, as I have my alert on, I hear every day. What you're doing is harming the planet, is bad for the planet, we have to take care of the planet, and so on. And I wonder whether this is a proper concept, something that we should read literally. Can there indeed be something that is good or bad for the planet as such? Or maybe it's just a metaphor, something that we say but we don't really mean, we want to convey something else. Maybe we are saying it metonymically, like it's not, in reality it's not bad for the planet, but for a part for the of the planet or an aspect of it. No? So to clarify my intentions is not to question what is good or bad for the planet. I think we have a pretty good appreciation of it through scientific research and the building of a consensus about the climate crisis. And what we need to do to solve this crisis, to stop the use of fossil fuels, to reduce our CO2 emissions, to protect biodiversity, restore ecosystems, so on. All this we know that we have to do. No? And we know that if we don't do that, probably we're in the risk of destabilizing the planet. This is from the famous paper Trajectories of the Earth System in the Anthropocene. And if we don't do all these things, the Earth might shift to a hotter state, a hotter regime. But can we say that this is a problem for the planet as such? And I think that's something that I hear very recurrently, is that, well, we say it's bad for the planet, but in fact, the planet doesn't care whether it's hotter or warmer. The planet and life on the planet has existed for possibly 4 billion years, and it has done so in very different regimes. It's had different ecosystems, it has been hotter and colder. So whether it's hotter and colder is not really a problem for the planet as such, but possibly for us, for our civilization, or for our comfort. So this is a recurring idea that I've heard many times. Even when I open this topic with many people, they say, yeah, in fact, the climate crisis might be even good for the planet, because in this way human civilization or even the human species will be wiped out, and the Earth will be better off after that. So I do not intend to entirely solve this question, but at least provide some hypotheses and some proper context to discussing it. So let's hope that we can get into it. I am not the only one trying to think this, and here I mention two existing approaches to it. One is the one of planetary health, proposed by the medical journal The Lancet, where they provide a definition of planetary health linked to the health of humans and of human civilization. And I think this is a very good program for research, as indeed we find that our health is linked to the well-being of the ecosystems that surround us. And for instance, the COVID crisis that we had recently is very well understood in this context. So I think this is a very sound project, but it doesn't satisfy what I'm asking, because in fact it's linking the health of the planet to the health of human civilization. But as I've said, the span of life of our living planet is much bigger than human civilization, so it is not clear that just defining it in this way we can properly understand what is a good state for the planet. One that is a bit closer to what I want to do is this idea of planetary well-being. It's a different definition. And these authors, it's a multidisciplinary paper. They defined planetary well-being as a state in which the integrity of the Earth system and ecosystem processes remains unimpaired to a degree that lineages can persist to the future as parts of ecosystems, and organisms can realize their typical characteristics and capacities. So again, although it refers to the integrity of the Earth system, in the end it is referring to the integrity of existing ecosystems and organisms and their permanence. And again, I think this gets close to what I intend to do, but and it gives a sort of guide for action, because we want to preserve existing ecosystems and lineages and avoid mass extinction and so on, but it sort of lacks this understanding of the Earth as in a long-term geological scale. It just gives a reference point from today, what can we do that is good for the planet, but I don't think it's a satisfying definition of planetary well-being. So how do I plan to address this? When I'm talking about the planet, indeed I am referring to the whole planet understood as a system. This is the perspective of Earth system science, which has many different fields within it, which is a fairly recent research program. And when Earth system science refers to the planet, they refer indeed to a system which is composed on the one side by the biosphere, that is the whole, all organisms and that exist on the planet, but also the atmosphere, the hydrosphere, the lithosphere or geosphere, and so on. So the planet as a whole. This perspective of Earth system science historically originates, and this is very well acknowledged by Earth system scientists, in the Gaia hypothesis, the idea that this not only is a system, but is a system of a particular kind, a living system. Although in Earth system science, we don't today find many reference to this kind of metaphor of the Earth as an organism. So, are the Earth system and Gaia two different things, or is it the same thing? So, some authors who have thought very carefully about this, I'm talking about Tim Lenton, who's a climatologist, Sébastien Duteuil, which some of you know, who's a philosopher and historian of science, and Bruno Latour, the philosopher and sociologist of science, have provided a definition of what is Gaia, what do we call Gaia, which is life plus its effects on habitability, meaning that life has altered at least some aspects of the planet in a way that has allowed it to persist, and we refer to Gaia as this system that is formed by life plus its effects on its surroundings. The implication, at least for the authors of this definition, is that in the measure that there are parts of the Earth system that have not been modified by life, they wouldn't be part of this Gaia system, but only of the Earth system. So Gaia would be a part of the Earth system. However, I'm a bit skeptical of this reading, because in fact, if we examine the Earth, we find that it has been transformed by life very, very deeply, to the point where it's very difficult to find a part of Earth which is outside of this Gaian system. So I am here is a picture of the Earth on the inside. And the Earth is very different from every other planet we know in many aspects. One of them is, for instance, plate tectonics. So the fact that the crust is sort of cycling constantly through the mantle in a sort of Bénard cell, you know, self-organized dissipative structures that adopt these hexagonal shapes. In fact, the continents and the plates can very well be seen as these sort of Bénard cells, which help to dissipate the energy that is produced in the inner core. They dissipate it in a quicker way by this kind of self-organized Bénard cells that take place in the mantle, and this process, which, as I say, is original, we don't find it in other planets. Its origins and its structure it can only be understood because of the presence of life on the surface, which has maintained water in the surface of the Earth, has made the crust more brittle, and through many different interactions between, let's say, the biosphere and the lithosphere, has at some point during the Earth's evolution onset these plate tectonics, which in their place play a key role for the long-term sustainability and regulation of the Earth. So this recycling of materials is the basis of what we call the slow carbon cycle, also sometimes referred as the inorganic carbon cycle, but I don't think that's a good term to call it the inorganic carbon cycle, not only because I see the Earth as some sort of organismic thing, but also because in that geological process already organisms and life play a key role by sedimenting carbon and allowing it to deposit in the seafloor. This is mainly done by microorganisms, and it supports this cycling, which the slow carbon cycle is also one of the key elements of the thermoregulation of the planet. So then there's also the quick carbon cycle, which is more happening in the surface and which sort of modulates that thermoregulation. Even, I think, quite strikingly, the magnetic field of the Earth is also a feature of our planet that we don't find in other planets. Other planets have magnetic fields, but they tend to be much weaker, and in fact, the way this magnetic field is produced is precisely because of this cycling of materials. There's some metals somewhere around here that are turning, and that's the most likely explanation for the magnetic field of the Earth, which also is key for the sustaining of life on the surface of Earth. So I wanted to point all this out because before we rush to say, yeah, the Earth is an organism, we must say that it's a very strange, if we want to call it an organism, it's a very, very strange organism. We don't know any organism which does all this stuff. So I prefer to say that the Earth is not an organism, although that, of course, would depend on the kind of definition of organism we defend. And on some, if we take von Bertalanffy's definition of organism, I think that we could say, yeah, the Earth is this kind of self-organized entity that maintains itself far from equilibrium and so on. It would be an organism in that sense. But I think it's more useful to see that organisms exist at a particular level of the Earth system, and they have some common properties among themselves that we don't find in the Earth as a whole. So to me, to sort of flatten the ontology of the Earth system to say, yeah, at each level things are organism, I think it's not useful. But again, that depends on what our definition of organism or of life we want to propose. But indeed, we need to point out that there are some key things of the Earth that we don't find in any other living being or organism. It doesn't use external matter, so all the matter that sustains its metabolism is recycled. That this means, as Margulis pointed out, that the Earth eats its own waste, and that's quite a strange thing to do. It exists in a purely abiotic environment, and we don't know of any other organism which can exist in an abiotic environment, because of course it is, or it includes the sum of all biotic entities that we know. And also, and this will be very important to what I will be presenting, it transforms in creative ways in an open-ended way. So we don't know what is the shape of the Earth, like the ideal shape of the Earth, because we find it in many different states, and it evolves in a creative way without a sort of predetermined type or genetic code. And also, it is no sé si se va a apagar la tele. Okay, it is unique, and this poses also some methodological problems. How to understand a system when it is the only one of its kind, and we cannot sort of operate by induction, examining many different examples of it, and sort of abstracting the common characteristics. So some theories try to address this problem by thinking about living exoplanets and talking about the evolution of biospheres in general. But to me, there's a problem with this because we don't have a single other example to work on, and this really complicates the possibility to work through induction and really forces us to work in a very situated way within the planet. We'll see about this later. So my preference is to say that it is a sui generis biological individual, that is a biological individual of a particular kind, of which it is the only example, so that's why it's sui generis, and the kind will be a living planet. So it's not an organism, not an ecosystem, but a living planet. But this is just to give some background. I don't need you to accept this definition in order to accept what I will present later. So indeed what first Gaia theorists and then Earth system scientists observed is that there seems to be a self-regulation of the Earth in a way where the Earth has maintained itself within the limits of viability of life. And this is very clear through the example of the faint young sun paradox, which comes from the fact that the sun has increased its brightness through the history of the Earth. So this is the whole history of the Earth. So at the origins of life, the sun gave us much less energy than what is currently given. And if the Earth at its origins had had a similar atmosphere to the one it has today, the global mean temperature of the Earth would have been below the freezing point of water, and we couldn't have had the origin of life. So, in fact, we found the temperature of the Earth. We can reconstruct it as always being around here, which is in the range where life is is viable, is possible. So in a way, the atmosphere has adapted to maintain this sort of, or in a way that maintains this sort of viable range of temperatures. So this is about, okay, this is the range where, let's say, life doesn't die. But then, as I'm interested in discussing the current crisis, is it, when we talk about crisis, is it because we will go to a temperature that is outside of these limits of viability, and in this way life will get extinct? Or rather, we are talking about a variation within this range? And I think that's the second is the truth. But then the question is whether within this range there are better and worse states. States, let's say metaphorically, that are healthy and unhealthy, functional or dysfunctional, precarious or more viable, whatever. So I will not start by a discussion on all those concepts in the organizational literature, but rather try to show what this sort of a good state for the Earth looks like, to try to convince you that there are some particular states which appear to be better for the Earth, and then try to extract an idea of what does better for the Earth mean. So I think that only then can we use theories of biological organization to show how this normativity or this preference arises. So I will base myself on some results from Earth system science, or more precisely from paleoclimatology and cyclostratigraphy, as you will see, to just make some sense of what global warming means. So I will start by James Lovelock's assertion that Gaia likes it cool. The idea that the Earth has a preference for cool states. And I say cool and not cold because it's not the coldest the better, but rather a temperature that is above the freezing point of water, but still close to it. So cool, but not super cold. Indeed, a drastic reduction of the temperature below the freezing point, as has happened at least a couple of times during the Earth's history, would be catastrophic for life. But before going on into this, I have to say that James Lovelock himself sort of backtracked on this idea, and at some point said, I didn't really mean to say that Gaia likes it cool, because that's sort of anthropomorphizing Gaia, which to me is a bit disappointing that he said this, because it is not only humans that have preferences. In fact, I would say that it is possibly the most basic phenomenological character of living things is that they have preference. So if he indeed was so invested in this idea that the Earth has a preference, he shouldn't have, that the Earth is living, he shouldn't have abandoned this idea that it has a preference. But to be clear, when I say preference, it's not just that it tends to a particular state as a physical system who can say it finds its equilibrium in a certain point and so on, but in a way that it has a sort of moral connotation that is good for the planet in some sense. So why did he say that Gaia likes these cool temperatures? First, before I go into that, to understand it, this idea that Gaia likes it cool might be a bit counterintuitive, not evident, because to us it's apparent that actually in our planet life flourishes better in the warmer regions. It's in the tropical regions where we see more abundance of life, and in the polar regions and so on, life is more scarce, and we experience the same thing during the year. No? It's in the spring and summertime when life flourishes, and in the winter life is sort of dormant. But indeed, and I will mention this, there are some measurements that Lovelock provided and have been partially confirmed to say that indeed life has been more abundant in cooler periods. So this paradox to me already points to a sort of systemic property of the Earth. It's not that in a particular place it's better to be warm. Indeed, the best place to be alive would probably be the warmer region in a colder planet. But indeed, this property of the planet as a whole is what we are interested in. So why did he say this, that Gaia likes it cool? Well, first he starts from a definition of the health of Gaia as the abundance of life. To me, this is insufficient. We will go back to this, but more than this definition, I'm interested in why did he thought that these periods were healthy? As I said, one reason is that he measured the traces of marine life in the glaciation and found that there were signs that life, the production of DMS was more abundant at that time. Also, the colder periods, so like during the Pleistocene, the recent ice ages, the continents were more exposed, and in the measure that life is more abundant on land, there's more biomass on land than on the sea. To have more continents allowed for more biomass and more abundance of life. But another way to understand this is that, and indeed here he refers not to the temperature but low carbon dioxide, which correlates very strongly to temperature, as you know, because of the greenhouse effect of carbon dioxide in the atmosphere. And when carbon lies in this carbon dioxide state in the atmosphere, is in a sort of in an inert, non-organic state. As life is mainly composed by carbon, when there's a lot of biomass, there's a lot of carbon that is captured in biomass, and so there is less carbon in the atmosphere. But this is in a very generic way, just to understand that, because of course, indeed, most of the carbon that is today in our era captured in the Earth, it's underground because of the Carboniferous period and the fossilization of organic remains and so on. So it's not necessarily part of the living surface of the Earth. So to me, a better understanding of this systemic property of the planet preferring a cool state is looking at it through a thermodynamic lens, and here I refer to this work, where indeed low temperature of the planet can be seen as a low entropy of the system as a whole. This intuitively sort of relates to the very definition of entropy, at least in the sense that an increase in entropy, an increase in temperature leads to an increase in entropy. But also in chemical disequilibrium terms, indeed the fact that there's more organic matter coupled with oxidized atmosphere represents a chemical disequilibrium. So it means that the system and that aspect of the system is away from equilibrium. It's very reactive. There's stuff that can happen, no? Work that can be done. No? So from this point of view, and referring to Axel Claydon, it will seem, I will not reconstruct his whole study, but it will seem that it is in these cool periods, it would be a cool period of Earth, or a cool state of Earth, which would seem to have the maximum rate of mass exchange and the maximum rate of dissipative activity at the planetary scale. So this more far from equilibrium state is sort of pushes forward the limits to energetic activity on the Earth, which includes obviously life, but also atmospheric events and so on. They can be more powerful because of this general far from equilibrium state. So a cool Earth would be able to do more things. And here I'm referring not simply to the activity or the abundance of life, but of the system as a whole. It seems to be more dynamic when it is in this low entropy state. This is, of course, the correlation between all these things is not linear and it's not direct. I mean, there's a high correlation between more atmospheric CO2 and a higher temperature. They really look the same, the graphs of the temperature and the CO2. So this would be the more entropic state and the less entropic state, less atmospheric CO2, more oxygen, a lower temperature, more abundance of life, low entropy and more work capacity would represent a more powerful Earth, and the shift to more atmospheric CO2, less oxygen, a higher temperature, less abundance of life, higher entropy and less work capacity will all go together. But as I say, this is, I just put this out to help situate the concepts, but we really need to see the Earth concretely to see whether this correlation really sticks. No? So I will indeed go through a series of graphs that show the history of the Earth, going from the most extent, the whole history of the Earth, to our current period. So this first graph represents the whole history of the Earth, so over its 4 billion years, and the reconstructions show that indeed the levels of oxygen have overall gone up, not always up, they have gone up and down, but overall they have the recent period we're in, which is, this will be the Phanerozoic, so the time where we have complex life on the surface of Earth, has higher oxygen than all the periods before it. So now I will zoom to this period and move to the temperature. So you allow me this shift from one magnitude to the other. This is a paper that was published only in September last year, which is a reconstruction of the whole temperature over the Phanerozoic period. And I have to say that this paper introduces some change because they have reviewed the proxies for temperature back in the Paleozoic era and so on, and they have sort of made it cooler than we thought. The tendency until now seemed to be that we thought that even during the Phanerozoic era, the temperature had become globally cooler. Now it would seem rather that it has alternated between cooler states and also hotter states without necessarily a very clear tendency between both. But then I will zoom again on this period. So this is the Cenozoic, is the time of mammals, of which we have more precise estimations of the evolution of temperature, and you can already see the downwards trend, which is very clear during the Cenozoic. This is better studied and so on. It's clear that tectonic events had an important role in this cooling of the Earth, although the interaction between life and tectonics is not one-directional. So and this is very clear in many lines of research that there's a mix or a interconnection between both. So indeed, through the Cenozoic period, life has become, the Earth has become cooler, reaching what interests me here, which is the Quaternary period. So it's the last 2.5 million years. A period which is characterized by the fact of having ice sheets both in the South Pole and in the North Pole. So that's what defines sort of the Quaternary in geological terms, is that we have ice caps on both poles. So this only happened recently. It had happened before, but in the Cenozoic it only happened over the last 3 million years. And this is the temperature. So the Quaternary starts here, and this is the temperature that we have over the last period, which you can see is oscillating, and this will lead me to my next part, as indeed, and this happens through the geological record. If we look at it closely, the temperature is behaves in a sort of oscillatory way, alternating colder and warmer periods. So this takes me again back to Lovelock, because as you know, the most recent, which I have not represented here, the most recent geological period, in fact, is the Holocene. So this is the last 12,000 years. They are sort of a warmer state after the last glaciation. And Lovelock said, referring to this state, that we might want to understand it as a sort of already feverish or pathological state, saying that, well, Gaia is more comfortable here. This is a sort of fever that it has caught, which is comfortable for human civilization, but not necessarily for the Earth as a whole. This is what when he explains the Gaia likes it cool, he also explains this idea, the Holocene as a sort of feverish state. So in my second part, after this whole review of temperature and thermodynamics, I will go into this thing about the oscillation of temperature in Earth's history, where, which is, as I said, is a feature of, through the geologic record, we see the kind of oscillation. Some of you came to Zumaya a couple of years ago and we visited this. It's all over the Basque coast. And it's the trace that this was possibly 80 million years ago or 60 million years ago. The Earth oscillated between two states very regularly, and this left traces in the marine sediments, depending on whether the sea was higher or lower. The deposits were different, and this has left this trace. And what geologists have discovered and found is that this oscillation is quite well synchronized with changes in the rotation of the Earth, and this in three ways. So, as you know, the Earth turns over itself, and it does so. Its axis sometimes points like this, sometimes points like this, and it does so in a more or less pronounced way, and all this changes periodically because of the interaction of the different bodies in the solar system and so on. So there's a regularity of 26,000 years, 41,000 years, and also the orbit of the Earth changes its eccentricity with a regularity of 100,000 years. So the geologists discovered, and it was Milankovitch who first hypothesized this, that these changes corresponded to an influence of the sun on the Earth. And I have to say that this was one of the first, this fact was one of the first objections that Margulis received when she presented, before even publishing their paper, when she presented this as a scientific meeting. A geologist said, no, of course the Earth doesn't control it, regulate its own climate. It's the sun who does it, because we know the Milankovitch cycles is pretty well confirmed. But to this, I think one can object that synchronicity doesn't imply causation. We know that the Earth, the climate of the Earth doesn't necessarily affect its rotation. We know the reasons for the rotation. But the fact that its internal rhythms are synchronized to these external cues doesn't mean that the external cues actually cause the changes. It might be that they are caused, but it might also be that the synchronization is more like what living beings do. Every living being, I think, that we know, also synchronizes its internal processes to external cues coming from the sun or the moon or the seasons, in a way that is functional to its own metabolism, because it allows it to order, to orchestrate its metabolic processes in an extended way through time, and in this way achieve stability or homeostasis or maintenance integrity of how you want to say it. So of course, this can be shown experimentally in plants, because you take away the changes in solar radiation and you see that there seem still some traces of this rhythm. We cannot do that for the Earth, but it's an hypothesis for research which actually relates to many of the researches that are being done, particularly to understand the most recent variability of the climate in the Quaternary, which I will go to now. Looking for more endogenous processes that cause this cyclicity, and how they relate to the very metabolic structure and organization of the Earth as a whole. So from this point of view, the alternation, going back to Lovelock, the fact that the Earth is in a warmer state needs not be seen as a destabilization or as an anomaly, but rather as part of a B-stable stability. But here we move to another problem, is that in the Quaternary period, over this last epoch, there is a shift around 1 million years ago to a slower rhythm. So if typically in the geological record we find this kind of 20,000 or 46,000 rhythmicities, suddenly at some point during the Pleistocene, the rhythm has become slower, and the Earth seems to have adopted this 100,000 year cycle. And this is a big problem for geologists, and you can find many papers discussing and trying to provide models to how that could have happened, particularly because this 100,000 year cycle is the one which provides the less variation in radiation. So it's, let's say, a very weak signal that is sent from the sun to the Earth. These two are much stronger, and however, suddenly they seem not to influence the Earth's climate anymore, but it's actually the weaker signal which is influencing, or it's correlating to the climate of the Earth. And as I say, there are many hypotheses and many different models to try to explain it. There's another additional problem to this, is that there's this paper, for instance, a causality problem for Milankovitch, which shows that in fact, at least in some cases, the change in the climate comes before the change in the eccentricity, or the onset of the change that can be measured in the surface of the Earth, and so on. So to me, what this suggests is that the climate of the Earth has become more endogenously driven in this last period. In a way, the Earth has overcome the influence of the stronger Milankovitch cycles. It self-regulates in a way where these changes in solar variation do not affect it as it used to, and it has adopted this slower pace. No? So I add this to the characterization of what a cool, now in double sense, not only cool as cold, but cool as good, as nice. Or, as I prefer to say, Gaia likes to chill, so not only to be cold, but also to be chill, to be relaxed, or less agitated, let's say. No? But I mean, we can go on discussing about this, because I would not like to imply that because of this slower rhythm, we can also say that the climate of the Earth is more robust. Because of this endogenous spacing, the climate of the Earth is more stable and less affected by noise or signals and so on. It has indeed become less affected by the signals of the sun, but it's also in a state which is more vulnerable to changes coming from within. So because of the rising luminosity of the sun, to maintain a cool temperature requires lower and lower levels of CO2 in the atmosphere, and this also means that a certain amount of CO2 that is added to the atmosphere can have a bigger impact. So indeed, we are in a sort of critical state for the Earth also, or as Andrew Watson put it, we are not in a good time. It's not a good time to mess with the Earth's climate. We didn't choose a good time to mess with the Earth's climate because indeed it's sort of in a critical state. So in a way, I think highly complex, highly endogenously driven, sustaining a big biodiversity and complexity of life, as we will see in our next point, but also at a point which is very, very critical and not easy to maintain. No? Also because I refer to CO2, but also the North Cap creates a lot of positive feedback because it melts quickly, no? And it has an albedo effect, so it keeps the Earth cool, but as soon as it starts melting, the albedo effect is reverted. So it creates a sort of positive feedback also for the climate of the Earth. No? So I have mentioned two aspects of the Earth system through its history, and particularly in the Quaternary period. One is the temperature, the other is the endogenous pacing of climate change. And I think if we talk about the Quaternary, we cannot avoid talking about something very special that has happened in the Quaternary. So indeed, biodiversity has risen through the Earth's history, and particularly through the Cenozoic, and in the Quaternary we're in a period of high biodiversity. And one aspect of that biodiversity and complexification of the Earth is the appearance of new species with new capacities that we had not seen on Earth before. So indeed, it is in this last period that we see the evolution of hominins and the appearance of Homo sapiens with all its original capacities. And one way of explaining the evolution of humans and its relation to climate is the fact that as we've had this very strong climate change, this has forced adaptation, and indeed we can track many key evolutionary changes generally in species to moments of strong climate change, but also that the Earth sustains a highly complex setup with complex ecosystems in which humans have evolved as a sort of apex predator. So is this, I include this in the characterization of the state because to me it points to a capacity of the Earth to evolve and to create new things, but it's not clear, and I don't think this is we can give a definite answer to this, whether these capacities that humanity has actually contribute to the autonomy of the Earth system, or the opposite, they take it to a crisis of the Earth system. And to me this is a sort of open question that we have nowadays, whether the evolutionary process that has led to us actually will result in something that is better or worse for Earth. I think that's a way of understanding our current predicament. So to wrap up on this definition of Earth well-being, I refer to the increased thermodynamic work capacity, the increased endogenous pacing of climate change, and new emergent capacities. I put it with a question mark. And all of this, to me, suggests a sort of increased autonomy of the Earth system. So an increased capacity to perform work, to self-regulate itself, and to do things that it was not able to do before. So if we want to give a definition of well-being of a system, I will refer to this paper I cited at the start, which is the functional integrity of the system, or in other words, the integrity of the critical system processes that allows the system to continue to exist and realize its system-specific characteristics and capacities. Well, I think that my definition of well-being has something to do with this, but it should be clear that the system-specific characteristics is something that is not predetermined, but which are sort of acquired through time and through the time of evolution of this system. And I contend that these capacities that it has acquired sort of expand the Earth's autonomy and its domain of action, its capacity to do things and to self-regulate and so on. So this definition of well-being, I think in the autonomy tradition, it refers to sort of some intrinsic properties of the system, but to some extent, I have included in that intrinsic capacities our own existence, and so I think that the definition is also partially observer dependent, because it's us observers who are given that definition and also wondering what will happen to us and what the Earth has in stock for us. No? So this has sort of been a sort of empirical assessment of what a highly autonomous, and I sustain the well-being state of the planet looks like. As you know very well, organizational accounts of function or malfunction relate their analysis to the integrity of the system. And I think that after this we can see that there are several levels of integrity, which I will present very, very briefly. To me, in the first place, the Earth, it exists as a physical object, whether it has life or not. So even if life disappears from it, it will still be a physical object. And in this sense, it's different from organisms, which if they die, they sort of disintegrate and tend to disappear. Well, you could say that a dead Earth, maybe it would be like a snail. If it dies, it still leaves a shell behind. No? So that's one first level of persistence or integrity. Then it has established a global planetary self-sustaining system through all its history, so it has remained within the boundaries of viability, although it might be also that at some big extinctions it has abandoned this state, and so that there have been several Gaias. It could have been that in some great extinctions life survived only in small pockets, and later it recolonized the planet again and created a sort of global system. But in any way, within these boundaries, it has moved, as I propose in this paper, to a state of heightened autonomy. I do not imply that this move is necessary or it's an inevitable physical tendency or something that is predetermined, but that studying our recent period, we find that indeed it is in this kind of state of increased autonomy, that this state maintains its stability through a sort of oscillation and therefore a bistable state. And it is this last regime and this bistable state which is sustained by what Earth system scientists call tipping elements of the Earth system. So the Amazon rainforest, the monsoons, the Atlantic current, and so on, they are defined by Earth system scientists as, I forgot to include the reference here, that is the tipping elements paper. They sort of constrain each other in a way that maintains the system in this, I defend, highly autonomous state. So indeed, we are now in a sort of moving out of this state. Whether we can define this as planetary malfunction depends on how we can conceptualize, I think, these different organs or constraints of the Earth system. But what is clear is that the current levels of atmospheric carbon dioxide put us outside of what were the limits of the Quaternary period. Temperature and the melting of the ice cap lags a bit on CO2, so it will be a few years till we see the effects of this high CO2, but the tendency is for the ice caps to quickly disappear unless we are able to revert that. So this alteration, this sudden change has been called the Anthropocene. The global geologic society has now rejected this idea of the Anthropocene as a new geological era, in my view correctly, because what we are witnessing is rather a geological event, something that is happening, but not yet a sort of stable state. We don't know what the stable state of the Earth will be in 1 million years and so on, and geology only works in those big time scales, but it does allow us to situate the kind of crisis we are in. And that is all. So there you go. This is the poster I presented in London, which is a sort of a synthesis of the same idea. There you go.